Okay, so that means the angle here becomes 90. Now when it is 90, cos 90 is what? 0. So that means when I fix my cos 90 here, it will be 0. So that means here the torque will be equal to 0, or T will be equal to 0. Basically, that is what it means. That is what it means. So I said when it is tilted at an angle theta. Now, so you know that there's an angle from there. Now, when this angle, the angle from there is 90, then that means your T will be equal to 0. Now, when it is not 90, then that means if it is 30, then that means it's going to affect it. But when it is 90, then that means your angle is cos 90 is 0. So 0 by the binding or will give you 0. Now, however, if the plate is parallel to B, which is the breadth of this core, of this iron core, then that means there won't be any angle formation. As a result, the angle here will become 0. And when the angle is 0, then that means cos 0 is 1. So we are going to get T is equal to binding like we did last week. Basically, that's what it means. So that's what we wanted to arrive at. Now, it is this same principle that was used to make what we call the galvanometer. The galvanometer. Now, when we talk of a galvanometer, it's an instrument which is normally used to detect current and potential difference. So a galvanometer, way back in school, we've been learning galvanometer, but most of us don't even know what it is. No, most of us haven't seen it. What we are always abreast, or what we always know, is the ammeter and the what do you call it, the voltmeter. Now the galvanometer can act like an ammeter and can also act like a like a voltmeter, but it is used to detect current and potential difference. Basically, that is it. Now, when the galvanometer is modified to measure current flowing, it is called the ammeter. So when the galvanometer is an instrument, when it is modified to measure current, then that means it is called what do you call it, an ammeter. Now, when it is also modified, and if its full scale deflection measures current in milliamp, it is called. Now, when it is when what it measures is in milliampere, then we can call it milliammeter. That is when the units, what it measures is in milliampere, then we call it milliammeter. On the other hand, if a galvanometer is modified to the level where it can measure what we call the voltmeter, then we call it what do you call it? We call it the voltmeter. Now, when it also measures in millis, then we can call it millivoltmeter. Millivoltmeter. That is when it is calibrated in such a way that it measures in milli. Then we call it millivoltmeter. Millivoltmeter. Now, the ones we've been seeing, the multimeter. You realize that the ones we've been using at our labs are multimeters. I have one. I don't know where I played. I think someone has come for it. A multimeter. That one has all of them. It has both the ammeter on it. It has a section that can measure the voltmeter, and it uses all the same principle, the movement, the torque principle, and all those things. And so that is it. And so that's why it is called multimeter. That means it has a lot of meters on it. It can measure the resistance in ohms. It can measure the current. It can also measure the what do you call it? The voltmeter. It's a form of a galvanometer, but this one it's multi-configured. Let me put it that way. It is multi-configured. And so you have just 1 meter or one system having been able to measure the ohms, what do you call it, the resistance, being able to measure the current, also being able to measure the voltage or potential difference across a conductor. Basically, that is it. Now, that is it. So it is made up of a coil. So the moving coil instrument consists essentially of, and it consists essentially of a rectangular coil of many turns, which is wound around a former. That is it. And so it also has a coil, just as we studied the other time when we are doing the talk. You realize that the talk we considered a rectangular coil, something like this. So that is how it operates, and it has a powerful radial magnetic field between the curved poles pieces N and S. And these are things that I'll just let you go and read because they are what do you call it? They're a little bit technical or something. And you also have a soft iron core in it. And so it's also operates on that magnetism principle, like we did last week. And it has springs to control the rotation of the coil. So the coils rotate, and the more it rotates, the more the magnetism is generated. And when magnetism is generated, it in turn also generate what you call the current. Basically, that is how it means. So that is it. Now, looking at its mode of operation and so on and so forth, we are saying that the soft iron coil or the cylinder produces a radial magnetic field. When we say radial, we are talking about a circular magnetic field or a uniform magnetic field in which the coil rotates. And so where the coil rotates, it creates, I've already told you, as the coil rotates, it creates that radial magnetic field. So that is basically it. I wish I could draw it, but that would be a long problem. So drawing would have been best. So it creates that magnetic field. So having it north side and the south side, basically that is it. And so we are just going to look at one or two the theory of the instrument. I'm going to just give you a formula that defines the theory of this thing. Then we are good to go. So the coil is situated in a radial field B, and when the current passes through it, the coil rotates through the angle theta. And so a coil is situated in the radial field. When I say radial field, in the circular field. And so when you look into the instrument, it has that circular path, and the coil, what you call the radial field. And in that radial field, that is where the coil is situated. Now, when the current passes through it, the coil will rotate through an angle. You know, I'm talking about circular here, so the coil will rotate through an angle. And the angle depends on the strength of the spring. It depends on the strength of the spring. Now, the torque and the coil, the torque on the coil, T is given by T is equal to NAB, which is the number of turns of the coil by the area, cross-sectional area. You know, we are talking about a circular path here, so we are talking about the cross-sectional area. We are also talking about the magnetic field, which is generated. In other words, the magnetic flux density, which is B, and the current, which is generated. So here the torque, considering the operations of the galvanometer, is given by T is equal to NAB, or in other words, Bani is the same thing. It's just a rearrangement. NAB or Bani is the same thing. And so that is it. Where N is the number of turns, A is the cross-sectional area of the circular path or the radial distance of the radial field of so that is it. And the B is the magnetic field density, which is created, which is the N is the current, which is generated as a result of that. And it has that. I told that the torque the other day when I was telling you, we looked at the torque here and this torque, the torque also here. But here we are talking about a circular path. So it is the opposing force torque is equal to C theta. And the C here is the constant of the springs, which normally depends on the elasticity under the twisting forces. And so that is it. So we are just going to look at something of that sort. So we are going to say that the Bani is equal to the Bani. So like the other day where we considered this part being equal to this part, but they are opposite. But here we are considering here being equal to C theta. C theta. And this theta is the constant of the spring, because in addition there's a spring in it. I wish I could draw it so that I can explain it better. And so that is it, but you can just read more. I'm just giving a brief of it. And so there's the constant of the spring in it, and there's the angle. Now, when you have something like this, then you can just manipulate it. If you want to find for the current, you just make I the subject. If you want to find for the number of turns, you just make N the subject. If you want to find for the area, you just make A the subject. So for instance, if I want to find for the current generated using that of the operations of the galvanometer, then that means this will be C theta all over BAN. All over BAN. All over BAN. That is it. So, and the above expression shows the deflection. It shows that the deflection theta or the angle is proportional to the current. And so looking at this, you can see that the angle is proportional to the current. They are all proportional. It's equal to. So as the current increases, the angle also increases. Basically, that's what it means. So that is it. So we can look at all these things. We can look at all these things. The rest is reading. We can all look at all those things. That is it. So I wouldn't want to. Now, if, for instance, if the galvanometer is upgraded to measure for voltage or PD, then that means the current here is equal to V is equal to IR. V is equal to IR. But I is equal to V all over R. So then that means you can also say V all over R is equal to C theta all over BAN. That is it. That is all about the operations of galvanometer. And I said that galvanometer is an instrument that is used to measure current and potential difference. Now, when it is upgraded, but normally it measures smaller current. Now, when it is upgraded to measure big current, or when it's upgraded to measure current, then we call it the ammeter. Now, when it measures current in millimeters, then we call it, or in millis, then we call it milliammeter. Now, when it's also upgraded to measure voltage or potential difference, then we call it voltmeter. Now, when it's measured, when it measures the voltage or the potential difference in millis, then we can call it millivoltmeter or millivoltmeter. That is basically, that means every value you get is in millimeters. Every value you get is in milli. What milli is, I think 10 raised to the power minus 3. Yes. So that is it. That is basically what it means. Now, today, from here, we are going to talk about electromagnetic induction. That's what we are going to do. Electromagnetic induction. Electromagnetic induction. Electromagnetic induction. Can I please explain about electromagnetic induction? Electromagnetic induction. Can I please explain about? Oh, someone should talk to me. Or any question? Any question? Now, let's do electromagnetic induction. Electromagnetic induction. Now, when we say electromagnetic induction, the electromagnet means electrical and magnetism. Basically, that is it, joined together. So, the flow of electric current as a result of magnetic field or something. Basically, that is what, or when placed in a magnetic field. So, we are talking about electromagnetic induction. Now, when we talk of induction, it comes from the word induce, to induce. That means when we are talking about magnetizing a magnetic material, you realize that we said some of the materials can be magnetized by induction. That is when you just bring the magnetic material close to the magnet, it can get magnetized. And we cited an example as those when you go to the centrist. They normally keep their, or let me say, when you go to the electrical shops, they normally keep their bolts and nuts around the magnets. Now you realize that it will get to a certain point in time when the repairer is working, immediately he touches the what do you call it, the screwdriver to the screws. You realize that it gets stuck to the tip of the screwdriver. That means indirectly I'm trying to say that the screwdriver has become magnetized just by bringing it closer to the magnets, or just by being in possession of the magnets, it just gets magnetized. And that is it. And sometimes it loses its magnetism over a shorter period of time. And so that is it. And so that form, you consider that as induced magnetism. So when you bring it closer to a magnet, those magnetic materials like the nickel, the ions and the rest, they get magnetized. And so we looked at magnetism by induction. Now, here we are going to talk about electromagnetic induction. Here we are going to consider the types of electromagnetic induction. We are going to consider the laws of electromagnetic induction. We are also going to consider the Fleming's right-hand rule and mutual induction, self-induction. I think that is all. Then we are done with induction. Then Our last topic we'll do is alternating current. That will be next week. Alternating current. When we are done with alternating current, then we are done with everything under electricity. Electricity is very broad. Then maybe you might go to electronics or atomic physics. That is it. So we are saying that the phenomenon, when a class ends, you join again. So we are saying that the phenomenon of flow of electric current in a conductor, when placed in a magnetic field by the relative motion of the conductor and magnetic field, is called electromagnetic induction. So the phenomenon.
That's right.
Oh, you can. So let me just. So the phenomenon, the phenomena, the phenomena of flow of electric current, electric current, electric current, flow of electric current in electric current in a conductor, when placed SP here, when placed in a magnetic, when placed in a magnetic field, placed in a magnetic field, placed in a magnetic field by the relative motion, by the relative motion of a magnetic field and this principle was first discovered by one scientist called Michael Faraday. So we are going to talk about the Faraday law. It was discovered by Michael Faraday after having series of experiments. So the phenomena of a flow of electric current in a conductor, or the principle, anyhow you want to put, the phenomena of a flow of electric current in a conductor when placed in a magnetic field, by the relative motion of the conductor and the magnetic field, is called electromagnetic induction. And so when you place a conductor in what do you call it, a magnetic field, and there's a flow of current, there's a flow of current, then as a result of their relative motion of both the conductor and the magnetic field, and we call it magnetic induction. Now he made a lot of experiments, and we are going to discuss some of the experiments. The first experiment he did was that he found a coil, and he connected the coil to a galvanometer. And so let me see if I can draw this one. So that is it. So there's a circuit, and this is a galvanometer. There's a sign for a galvanometer. Now let me, it's like this. It is not straight, it is tilted. Now, and it is connected to a coil or a solenoid. Then the arrow is the generation of current, and it is measured by the galvanometer. Now, when a magnet, so we are going to look at this. Yes, south, and here is north. That is it. So this one is a solenoid. This is a solenoid. Solenoid. Now I'm just going to draw all the three experiments, and when I finish, I explain it. The other one, the second one, this one, this thing is north pole of a magnet moving towards the coil. So you realize that the north pole is moving towards this coil. Let's call this solenoid. Now I'm going to, so that's the first experiment. I'm also going to consider experiment 2. We have just 4. I'm also going to consider experiment 2. So the experiment 2 is the same thing like this, but this one is straight. And so that is it. So this one too is a solenoid. There's a magnet. Now here the north pole of the magnet is stationary. In this case, the north pole of the magnet is stationary. Now from there to, let's also consider the last one, where the north pole of the magnet is moving away from the coil. Wrote to the Public Procurement Authority in accordance with Section 93C of Act 663 as amended to request for ratification of the procurement processes for the items. The statement said by that action, the Chief Executive Officer subjected himself to investigation and ratified the procurement processes. It added that as at the time the items were procured, the Public Procurement Authority and okay. Public institutions were not fully operational in compliance with the partial lockdown measures announced by the President on the allegation that an amount of 4.8 million Ghana cedis was spent. So that is it. So these are the three experiments we are going to consider. Before we finish, you consider another set of experiments. That's experiment 2. So these are the experiments Faraday, the one who propounded the theory of electromagnetic induction, did before he was able to propound this theory. Now you realize that a coil of wire is produced by winding the length of the wire around the hollow cardboard cylinder. Now the coil is connected to a center zero of a galvanometer. No, so the center zero of a galvanometer. Now, if suddenly the north pole of the powerful magnet, so the first one is the north pole of the powerful magnet, is pushed towards or into the coil, the galvanometer gives a deflection. So you realize that when this north pole is pushed towards this thing, you realize that according to the experiment, there's a deflection by the galvanometer. So the galvanometer gives a deflection while the magnet is moving, indicating. So as the magnet is moving, this one is giving, there's a deflection in the, what do you call it, in the galvanometer. Now the galvanometer gives a deflection while the magnet is moving, indicating that a current is flowing. So realize that when this is moving, this is there's a deflection in this, and realize that this shows that there's a current flowing, or the current is flowing. And so basically, when what they are just trying to mean is that when a magnet comes in contact with this, or when a magnetic flux is magnetic field is established, current is generated. And so this is not, and this is this one is, what do you call it, a solenoid. So when the north pole of this one comes into contact with this or moves closer to this, then there's what do you call, there's a deflection, which signifies that a current has been generated as a result of that. Now the current is said to be induced. So when that happens, we are saying that the current has been induced, and the induction is from this magnetic field. So when the magnetic field comes into this, it induces when it comes into it induces a magnetic field in this, which as a result also creates a current or generates a current. So the more this comes closer to this, the higher the current is generated, and as a result there will be a deflection of the galvanometer. That means the galvanometer is measuring the current which is generated. Basically, that's what it means. The deflection of this shows that it has moved from a certain point to a certain point. That means it is increasing. Basically, that is what I mean. If the magnet is kept stationary, so here the magnet is kept stationary. If the magnet is kept stationary, the galvanometer shows no deflection. So if the magnet is kept stationary, that means the galvanometer shows no deflection. That means the galvanometer is not moving because the magnet is stationary, it is not moving.